Last time on Mastering AMC 1012, we covered recursion, basically writing a function to solve problems for large values using small values. Today we're going to cover recursion in a way, except this time it's for probability. So basically, we use states when you're trying to find the probability of a win of a situation or some event happening in a situation. So when we encounter a states problem, let's take the following steps. Assign variables to probabilities of winning from different positions. Write equations for the probability of winning from each of these positions in terms of the other states. In terms of the other states is a key thing right here. Solve your systems of equations. And sometimes you can simplify states problems a lot by looking for symmetry. Symmetry is where positions where you have equal probability of something happening. And sometimes you also might have to use state recursion equations, which basically means the state at some position. But we'll explore more examples, and this will all make a lot more sense. Starting off with the simple example from the AMC 12. Tom, Dick, and Harry are playing a game. Starting at the same time, each of them flips a fair coin repeatedly until he gets his first head, at which point he stops. What is the probability that all three flip their coins the same number of times? So what are the possibilities we have to consider here? Well, what if they all roll heads the first try? That's a possibility for sure. Let's try the states approach. P, the probability that this will be true. P is equal to the probability, basically what we're trying to find, the answer, that they all three flip their coins the same number of times. So what is P equal to? Well, let's take a look at the cases. There's a 1/8 chance that they get it immediately right off the bat. They all roll heads and this is satisfied. So 1/8 chance right there. Now there's a 6/8 chance that some of them rolls heads, but some of them rolls tails. The reason it's 6/8 is because there's a 1/8 chance of rolling all heads and a 1/8 chance of rolling all tails, right? 1/2 cubed. And so there's a 6/8 chance of rolling some combination, maybe 2 heads, 1 tail, or 2 tails, 1 head. But in this case, the problem says, that they all three flip their coins the same number of times when they get their heads. But in this case, clearly, whoever rolled the tail will have to roll it extra times. Same thing when there's mixed. So this is not possible. It's never possible after this happens. 0. Now the final 1/8 chance, they all roll tails. In this case, what do? I mean, none of them rolled heads, so they all have to keep going, but also none of them rolled, all of them rolled tails, not just some of them. So nobody got their first head yet, so it's not uneven yet. Because you can see here that there's no unevenness between how many tails, because they all roll tails, nobody rolls heads, so none of them stop. So there's still a chance that they're able to flip their coins the same number of times. So 1/8 times. Now what do we do here? The trick for states is using what you're trying to find in your equation. Basically, when they all roll tails, it's like it's back to the start because they all are rolling their heads again and they're all equal footing. They're all trying to get it at the same time. It's just P, because those tails are completely unrelated to the next rolls. It's just a situation again where none of them have rolled heads yet. Oh, wow, one variable equation. We can do that, right? 7/8P equals 1/8. P equals 8/7 times 1/8 equals 1/7. And that's the answer. Isn't that cool? So to summarize, we wrote a states equation, we took the cases, some were 1, some were 0, and some took us back to the original p in the problem. And then we solve for p to get 1/7. Okay, now, if you were watching the series, you might remember this problem. Frida the frog, we solved this problem using complementary counting. Now, we're going to show you an even slicker solution using states. Let's do this. Frida the frog begins a sequence of hops on a 3x3 grid of squares. Okay, so let's say that our 3x3 grid, and we're given that we move one square on each hop, and we're also given that we're not allowed to move diagonally, and that if we reach the edge, we'll just wrap around. So essentially what that means is that if we hit an edge, if we're, let's say, right here, we go down, then we go down again, we wrap around to the top edge, as I mentioned here. For at the center, we begin with the center square, makes 2 hops up. The first hop would go here, the second hop would wrap around. That's true the other way as well. And we'll jump to the opposite edge, as I mentioned. And we're saying Frida starts in the center square, makes at most 4 hops at random, and stops hopping if she lands on a corner square. What's the probability that she reaches a corner square on one of the 4 hops? How do we do this with states, you might ask? There's 9 different positions, so do we need 9 states and that we're gonna have a 9 variable equation to solve? 9 variables is a lot. Maybe it's not a 9 variable equation. Maybe there's some symmetry. Symmetry, I mean, the corners, they're all corners. The edges, they're all edges in the center. Well, there's just one of them. Is there any symmetry? Well, all the edges are symmetric because they're adjacent to the center and 2 corners. And that's true for all of them. 2 corners and the center. What about the corners? Well, they're all adjacent to 2 edges. In the center as well, there's only one of them, so of course it's symmetric. And the reason that we don't care about which corner it is or which edge it is, because the problem literally just states reaches a corner square. It never says reaches a top right corner or reaches a bottom left corner. Just corner. And if we're dealing with just corners, then we might as well also deal with just edges. So what we're going to do here is now we only have 3 states. That's it. Edges, center, and corner. Okay. Now let's write some equations. So what's the probability that Frida will be at the edge after some number of moves? So let's say after n moves, what's the probability Frida will be on the edge? And this is just edge, and this is just the number of moves that has happened so far. What's the probability that Frida will be on the edge in n moves? How can you get to an edge? Well, you can go from the center. So the probability of reaching an edge, well, if you're on a center originally, then there's a guaranteed chance of going to an edge. So if it's on the center after n minus 1 moves, it must be at an edge after n moves. Okay, is that it? Anything else? What about corner? Oh, be careful here. Frida stops hopping if she lands on a corner square. So there's no way you can go back from a corner to an edge. It's just this. But what else? Can it go from maybe another edge to an edge? Well, how would that happen? Right? There's no edges adjacent to this. That's where the wraparound comes. The wraparound. To go down, you'll wrap around and come back to the top, another edge. So e of n minus 1, but this is not always going to happen. From here, it has four choices. Equal directions. There's the top, there's a wraparound, and two ways to go to the corners. So only one way goes to an edge. So it's actually just going to be 1/4 e of n minus 1. Interesting. Now, what about CEN, or center at n? What's the probability it will be at a center in n moves? So how can we get to a center? And here we're assuming n to be more than 0 in this case. We get to a center from an edge. You can't go from a corner, first of all, and second of all, you can't even move from the corners, so that we have to go from an edge. If we're on an edge, what's the probability of going to the center? So e of n minus 1, but it's not always guaranteed. From here, we have four choices. One of them is going back to the center. Two of them are just going to corners. And one of them is going to another edge. So there's only a 1/4 chance that it goes to the center from one of the edges. Okay. Now, what about corners? Well, we could write another equation, and just like we did earlier, but a key thing to know here is that e of n plus ce of n plus the corner of n, so the probability of being at a corner after n moves, they must sum to 1. Why? Because there's only 3 possible locations, so they must sum to 1. So we can actually just write this as 1 minus en minus cen, because it's just 1 minus the probability it's not at an edge or center. Okay, now we have these equations. What do we do with them? Well, we're asked to find after 4 hops. So we want 4. What's the probability? What is CE of 4? Or CO of 4 is what we really want. So let's just write that here and box it. We want CO of 4. The probability of being at a corner after 4 moves. Now, let's just iteratively calculate stuff, because we know E of 0. We know E0, CE0, and corner 0. Let's make a table. And this is a strategy when you have these kind of recursive states equations. Make a table. Let's write that here. Center, edge, and corner. Okay. And let's make another chart here. 0 moves, 1 moves, 2, 3, and then finally 4. Okay, so after 0 moves, basically, initially, where is it? Well, of course, the center. Nowhere else. It can be 1, 0, 0. It's not going to be at an edge or corner when you're literally starting on the center, right? After 1 move, what's the probabilities of stuff? Well, remember here, E of 1 equals CE of n minus 1, or CE of 0, plus 1/4 E of 0. Because E of 1 minus 1. E of 0 is 0, but CE of 0 is 1. So now it's 1 here. And CE of 0 is 1/4, or CE of 1 is equal to 1/4 E of 0. And the probability is at an edge in the beginning. That's 0. And the corner will also be 0 because 1 minus the sum of the other 2's. Now you can kind of see where we're going from here. What we're going to do is we're going to say that CE of n, so this point right here, CE of 2, is just 1/4 the probability it was on an edge on the previous turn. So in this case, it's just 1/4. Because there's a 1 probability of being an edge after 1 move. Now what about edge after 2? Edge after 2 is CE of n minus 1, or CE of 0, so, or CE of 1, I should say. The probabilities at the center after 1 move, which is 0, plus 1/4 the probability it's at the edge at 1. 1/4, edge of 1 is 1, so 1/4 of that, 1/4. And the corner is just 1 minus the other 2, so half so far. Okay, after 3 moves, we're making progress. After 3 moves, to be at a center, it's just 1/4 the previous edge. So to be at a center after 3 moves, 1/4 the probability of being at an edge after 2 moves. So 1/16. And the probability of being on an edge after 3 moves is the probability of being on a center after 2 moves, so 1/4, plus 1/4 times the probability of being on an edge after 2 moves. 1/4 as well. And it turns out if we add this up, that's 1/4 plus 1/16, which is, sorry, I erased those lines. 1/4 plus 1/16 is 5/16. So this will just be 10/16 because it has to sum to 1, which is just 5/8. Final step. Center 1/4 times the probability of being on an edge after 3 moves. So 5/64. And then edge is the probability of being on a center after 3 moves, 1/16, plus 1/4 the probability of being on an edge after 3 moves, so 5/64. Okay, so now all we have to do is add things up. 1/16 plus 5/64 is just 9/64, because this is 4/64. So now what's corner after 4 moves? The final answer. It's just 1 minus 9/64 minus 5/64. That's 50/64. Or 64 minus 14/64. 50/64, which is nothing but 25/32. And that's the answer. Let's recap really quickly, because this was a lot. First, what we did is we found the equations. And the equations turned out to be probability at an edge after n moves is the probability of being on a center after 1 move before that, plus 1/4 the probability of being on an edge 1 move before. Probability of being on a center after n moves is just 1/4 the probability of being on an edge the move before. Probability of being on a corner, well, we could have written the equations, but we noticed that these must add to 1, so we used some smart tricks, and it turned out to save us some computation here. And we might as well just write 25/32 here, and that's our answer. Okay, finally, we have Rashawn, Sylvia, and Ted playing a game. Each of them starts with $1, and a bell rings every 15 seconds. So they all start with $1. A bell rings after 15 seconds, at which time each of the players who currently have money simultaneously chooses one of the other 2 players independently. So, and at random. So they're not discussing or planning they're gonna give money to or whatever. It's just random. And they give $1 to that player. What's the probability? That after we ring a bell, 2019 times. You can probably guess the year of the test based on that, but after the bell has rung 2019 times, each player will have $1. So let's look at the example they have here. We have Rashawn, Ted, and Sylvia. For example, Rashawn and Ted may decide to give $1 to Sylvia, and Sylvia may decide to give her $1 to Ted. So Rashawn and Ted, they all have $1. Rashawn will give $1 to Sylvia, and Sylvia may decide to give $1 to Ted. That is the end of the first dollar of play. So they're just saying that after we give money, now one person has 2, and one person has 1, and one person has 0. In the second round, only the people who have money, so 2 and 1, would give next. Okay, let's try to understand what's going on here. Let's look at our initial state. Now you might be wondering, why is it called states? Because, well, there's many states that this problem can be in. The first state, also the starting state, they all have a dollar. $1, $1. Okay, interesting. So now, after the bell's rung once, what can we do here? So we're actually going to take a similar approach to the previous problem, kind of like a states recursion. So let's see what happens first. Let's say that Rashan gives $1 to Ted, and Sylvia gives $1 to Rashan, and Ted gives $1 to Sylvia. Now they all have a dollar again. It's back to the state where they all have $1. But like the problem mentions, it's not always going to stay this way. What if both Rashan and Sylvia give their dollar to Ted? Now Ted is rich, has $2, and maybe Ted gives his dollar to Rashan or something. So now Rashan has $1, Ted has $2, Sylvia has 0. This is $2, $1, 0. So there's a 1, 1, 1 state, and now we discovered that there's also a 2, 1, 0 state. So now we have to try to relate them somehow. But first of all, what about 3, 0, 0? Is that ever possible? Well, let's take a look at what happens when Rashan has $1, Ted $2, and Sylvia 0. Well, let's say Ted gives his dollar to Sylvia, and maybe Rashan gives his dollar to Ted. Now Ted is back to $2. It doesn't seem like we can ever hit that $3 mark for anybody. And why is that? Because even if they get both of the money from other people, they're not going to hit $3. But if they do, so they can't have no money, because even if they get $2 from each of them, let's say somebody has 0 and they get $1 from one person and $1 from another person. Now they have 2, but 2 is not 3. That would just go to this state. What if they already have $1 or even 2? Well, then even if they get $2 again, they're gonna have to give up 1. So net they only get +1. But let's take these cases separately. If that person only has $1, and let's say maybe they get paid by both people $1, they also have to give up 1. So now they're effectively still at 2 only. What if they already have $2? Now they surely should be able to get 3, right? One person has 1, one person has 0. The 0 can't give to anyone. The 1 can give to 2, but then the 2 has to give up 1. So still left with 2. So nobody can ever have $3. It's impossible. So now all we have to do is deal with 2 states and write a 2-variable equation essentially. But it's going to be a recursive equation, not just a simple x and y. Okay, let's write them. So we're gonna use a notation like this. P111. This is the state 111 at n. So let's just do that. So the probability that they're in the 111. Also, I forgot to mention, but these states are all symmetric because it doesn't matter who has $2 or who has $1. It's symmetric, and we're just asked to find after the bell is rung 2019 times. What's the probability? They'll all have $1. So 210 state, it doesn't matter who has it. It's symmetric because they're not really different. There's no different rules applying to anyone. So we use the notation P11n to define the probability that it's at the 111 state after n moves, and the P210 state to find the probability that we're at the 210 state after n moves. So now let's write our equation. P11n. Well, what if we're already at P111 at n minus 1? What will be the probability? Well, let's see. Rashawn, Sylvia, and Ted. If they all have $1, let's say they're the same anyways because of symmetry, but let's say Rashawn gives $1 to Sylvia. Now, Rashawn will give it to Sylvia. Whoops. So now Sylvia really has two choices here. Can give $1 back to Rashawn, or can pass on the $1 further to Ted. Let's take both cases. So if Sylvia gives $1 back to Rashawn, now Ted has to give his $1 to one of Rashawn or Sylvia. So in that case, Ted would be losing all money because nobody's giving him $1 and he's giving his $1 to one of Rashawn or Sylvia. So one of them would have $2 and Ted would have 0. We'd be at this state over here. But we're trying to find the probability that 111 state after n minus 1 moves. Okay, so maybe Sylvia does not give it back to Rashawn. Maybe Sylvia passes it on to Ted. Well, there's a half chance of that happening, so times half. Now, what does Ted do with that money? He can give it back to Sylvia. But then Sylvia would now have $2 because Sylvia gives 1 but gets 2 and originally has 1. But then Rashawn would be left with $0 because Rashawn is giving it up and not getting anything in return. So instead, Ted would have to give it to Rashawn, become a 111 state again. So what's the probability? Well, there's a half probability that Sylvia gave it not to the person who gave it to her, but to Ted, the other person, passing on further along. And then there's another half chance that Ted will not give it to Sylvia, but give it to Rashawn. So 1/4 chance essentially. That will be at P11n. Now, is there a way to get, what about the other case? What about from P20210 after n minus 1 moves? What's the probability of going back to the 111 state when there's already a 210 state? So let's say Rashawn has $2 now. Sylvia has $1 this time, and Ted has $0. So how can we go back to the state? Let's first consider, who does Rashawn give $1 to? If Rashawn gives $1 to Ted, now Rashawn will have $1 and Ted will have $1. But that means Sylvia will have to give up $1 but won't get anything in return. So Sylvia will give $1 to Rashawn or Ted, but won't get anything because Rashawn is giving it to Ted and Ted has no money to give. So that means it will end up back at 210. Instead, let's see what happens when Rashawn gives it to Sylvia instead. So just to summarize, if Rashawn gives his $1 to Ted, he would not have $1, but then Sylvia would be missing out. So now, what if instead Rashawn gives $1 to Sylvia, and then Sylvia gives $1 to Ted? That would work. But Sylvia could also then make Rashawn rich again and give him another $1. So for it to work, as we saw by our cases, Rashawn can't give to Ted, Rashawn must give to Sylvia, and Sylvia must give to Ted. There's a half probability Rashawn gives to Ted, or to give to Sylvia, and there's a half probability Sylvia will give to Ted, and not to Rashawn again. Times half, again, 1/4, wow. we could find what's P210n. But you notice anything a little bit strange here? We have P11n minus 1, P210n minus 1. What is true about P111n minus 1 and P210n minus 1? They're the only two states that exist after n minus 1 moves. So that means the probabilities must sum to 1. Wow. Wait, so this is just going to be rewritten as 1/4 times 1. Just 1/4. Isn't that amazing? So the answer is literally just 1/4. So we thought we had to write state equations and then look at 2019 recursion, but no. Using symmetry again, knowing that the probability sum to 1 just equal to 1/4. Okay, let's summarize this amazing problem. We have 111 state and a 210 state. And to be at the 111 state after n moves, there's a 1/4 chance. If we were already at the 111 state in the previous move, we go back to the 111 state. And there's a 1/4 chance that if we are at 210, we go to 1/4. So overall, because these probabilities sum to 1, since they're the only two states that exist after n minus 1 moves, the answer is just 1/4. And that was truly one of the best ways to end combinatorics and start algebra. In algebra, we have many cool techniques like Vieta's formulas, factorizations, polynomial manipulations, and telescoping, some of the most powerful tools on the AMC 10 and 12. But this will be in next time's units. You can check out the videos for algebra over here.